All right, so now I'm going to try to understand this result of Gurr and Marsden, which basically says that it's not possible for fixed time step integrators to simultaneously preserve both the energy and symplecticity. So we'd like to try to understand this in the context of Hamiltonian backward error analysis. So, so the result of Gurr and Marsden, so sort of basically sort of incompatibility of symplecticity and energy preservation. For fixed time step methods. Okay. Okay, so the result of Gurr and Marsden, it's like, which more or less says that symplecticity and energy preservation is incompatible for fixed time step methods, can be understood in terms of Hamiltonian backward error analysis. Okay, so if you have a fixed time step symplectic integrator, right, you know that there is a modified Hamiltonian by backward error analysis. H tilde of H. Okay. So if you require that this symplectic integrator exactly preserves the energy as well, then what you're basically saying is that the original Hamiltonian and the modified Hamiltonian Poisson commute, right? Then it has to be that the time rate of change of the original Hamiltonian evaluated along the flow map associated with the modified Hamiltonian, right? Or the flow of the modified Hamiltonian, right? That is, of course, just by definition, the Poisson bracket of H with H tilde, okay? And that has to be 0, right? So that's what I said, that the only possible way it's like for the symplectic integrator to exactly conserve the energy is for the modified Hamiltonian and the original Hamiltonian to Poisson commute. Okay. So this relationship sort of together with the assumption that H has no first integrals, except for functions of H, implies that H tilde, right, which is the modified Hamiltonian, is some function rho of H and the time step. Okay, so yeah, you don't really expect, if you will, it's like that, you know, if H, you know, the Hamiltonian, original Hamiltonian system is first integral, that it's going to conspire itself to be such that, you know, that first integral is exactly this modified Hamiltonian, unless there's some sense in which the modified Hamiltonian is a function of H. That's more or less what this argument is saying. Okay. Right, so where rho is a function, some function of H, and possibly H the Hamiltonian, and possibly little h the time step. Okay. So, all right, so why is this significant? This implies that the level sets of the energy I should say that. So this implies that on the level sets of the energy, right, which is that Hamiltonian is some prescribed value E, right, the modified vector field is just given by well, it's just equivalent to the sort of original vector field, which is the Hamiltonian vector field, right, up to a multiplicative constant. Let's call that rho prime. Okay, so what does that mean? So this is telling you that the numerical method, right, the symplectic integrator, okay, is the exact flow map of the original Hamiltonian, but for some rescaling, it's like of the time, if you will. Okay, and again, up to terms which are exponentially small. In H. Okay. So basically what that means is that up to terms which are exponentially small in H, right, our symplectic and energy conserving method would basically be solving the exact solution of the given Hamiltonian system exactly, okay, up to a rescaling of time. All right, and so this is exactly what leads to this result of Guerin-Marsden, which basically says that if you have a fixed time step symplectic and energy preserving integrator, then this is only really possible in general if it exactly samples the true solution up to a rescaling, right? So this leads to the result of Kerr and Marsden, right, which says that a fixed time step symplectic energy preserving method, right, samples the exact trajectory sort of up to a time rescaling. Okay, so another way to sort of think about this is that it says that fixed time step symplectic energy preserving method, samples possibly non-uniformly. It's like the exact trajectory. Okay, all right, and of course it's like in general it's like that's very, very unlikely. So so what this basically resulted in is a bifurcation, if you will. It's like of the class of symplectic integrators, or the class of geometric integrators for Hamiltonian systems, into energy momentum methods and symplectic momentum methods. Okay, so let's just stop here.